All right, welcome everyone to another Astronomy on Tap State College Quarantine Edition. My name is Michael Roderick, and joining me tonight, as usual, are Jacob Lund, Arvind Gupta, and Brianna Zwatsky, fellow Astronomy on Tap co-hosts. We are back during the daylight, which is nice. It is still sunny outside. It's not all dark and depressing. How about that? So tonight we are going to be talking about dark stuff. We are going to be talking about detecting dark matter, the crisis in cosmology with Dr. Carmen from Penn State and Taylor Hoyt from University of Chicago. So we are going to get started pretty soon here with making our astronomy drink. Then we will follow up with our first talk of the night by Dr. Carmen about detecting dark matter directly. Then we'll take a break for trivia with Arvind, astronomy in the news with Brianna, and then our last talk of the night, dark energy with Taylor Hoyt. So let's go ahead and get started and hand it off to Jacob. Jacob, I'm gonna have to stop you here. I don't know that your audio is going through. I'm not sure what's going on. I'm so sorry. I think my audio is going through, but we can't hear Jacob. Give me, you cannot. I'm sorry. Give me 1 second here to see what is going on. We were just talking about this beforehand, how we gotten into the sink of doing this so many times that we sometimes forget that there are things that we need to change. And I think that I just changed it. Can you say something, Jacob?
Testing.
All
We'll
right,
we'll
that
wait for
looks
the.
better.
Okay, now we can hear me.
Yes, all right, I apologize about that.
Okay,
You got to say everything
all
all
right.
over
So
again.
I'm going to rewind, pretend as though that didn't happen. So welcome to another Astronomy on Tap event. So tonight I'm going to be making a drink, and it's not one drink, but in fact it's two drinks. And you probably saw the long list of ingredients on the either before we tweeted or on our Facebook, or just on the slides before we started the event. And so you may have also seen our promotional image that said 10 things I love about astronomy. That's sort of the theme for the night. Don't worry, we're not going to have 10 talks. We're not going to put you through 10 astronomy talks, but we have two talks tonight, and the number 10 or 10 in binary is actually the number 2. And so our theme for the night, or a secondary theme for the night, is binary. And at least for me, when I think of binaries and astronomy, what else comes up to mind other than the great scene from Star Wars, A New Hope, binary sunset, Luke looking out on those two suns on Tatooine. Tattoo 1 and Tattoo 2 are their official names. And so tonight we're going to be making two half drinks. Both of them sort of slightly different plays off of a tequila sunrise. And this is going to be a binary sunset is what we're going to be calling these, or a binary tequila sunset, either one. And if you're making these along with us at home, we would love if you could share your pictures of the drinks that you make along with us. So feel free, when we're done, I'll try to remember at the end again to give a shout out. Feel free to tweet them at us or put it on our Facebook page or whatever. We'd love to see those. So I'm going to be making two drinks. If you only got the ingredients for one, you can make two half drinks, or you can make one double drink and just double everything I say. Don't worry too much about that. But I'm going to be making them kind of back and forth. So hopefully that maybe gives you a little a little bit of time because some of the ingredients are shared. So yeah, let's go ahead and get started. You will need some ice cubes, so those weren't on the list, but be ready to have ice cubes on hand. So let's go ahead and start. Oh, and one more thing I'll mention. I'm using martini glasses. I'm not going to be drinking martini glasses.
Jacob, I'm sorry. Stop. Your voice got robotic again. Oh. Yeah, we've had this before, man. Everything tonight is just crashing down on us, isn't it? Yeah, go ahead and say something again, Jacob. No, it's still. I think he said we'll be right back. Um, yeah, we've had this happen a few times. Sometimes his phone connects and audio somehow doesn't want to cooperate. Don't really know why that happened in the middle of uh, Jacob talking.
Hello, can we test my audio first?
Yep, you're good.
Okay. All right, and I have to get my video back. All right, so I don't know when this cut out. I'm not going to say all of that again for the third time. So we're going to go back to we're going to make drinks now. I'm going to use a martini glass because it's very narrow at the bottom and helps with the gradient from the dark red of the grenadine to the orange juice. I'm not going to be drinking out of a martini glass. It's a little cumbersome. I'm probably just going to pour it into another glass to drink out of, but I think it looks cool in a martini glass. So, okay. Whew. All right, so we're going to go ahead and start off. In drink number 1, we're going to take orange juice and we're going to do 2 ounces of orange juice. Oops, and I'm going to be spilling probably like crazy. Pouring into a martini glass isn't the easiest thing. Okay, and so we're done with orange juice. We can set that aside. And into that same drink, I'm going to be pouring in tequila. I have a silver and a gold tequila, so I'm going to be making one drink with silver and the other with gold just to make them a little different. But we're going to use 1 ounce of tequila, and we'll actually be putting that into both drinks. So 1 ounce of tequila in with the orange juice. And 1 ounce of tequila into the other drink, drink number 2. Okay. Next, we're going to be using our Corona. So both drinks get 2 ounces of Corona. And if you are a past trivia winner, you can open your Corona with the Central Pennsylvania Observer's bottle opener. And again, 2 ounces into each drink. So 2 ounces of Corona. And this does fill, I don't know if martini glasses have a standard size, but it does get pretty full, which is why I don't enjoy drinking out of it for this particular drink. So you'll have a good amount of some Corona left over. That's perfectly fine. Okay, so in this drink, we have the orange juice and tequila and Corona. In this one, we just have tequila and Corona. And we're gonna also add some simple syrup. And I'm gonna add just a little less than 1 ounce, about 3/4 or so. Depends on how sweet you want it. So I'm gonna pour that in there. And that was drink number 2. And at this point, I'm gonna give both of them just a quick little stir, especially the one with the simple syrup, since that's kind of a thicker consistency. It's not exactly the easiest to stir in here, but okay. And then this is when we're going to add in our ice cubes. So I'm going to put in about 2 ice cubes in each because that is about the right amount. Ooh, actually, before I do that, I forgot. This one also gets lemon juice. So we're gonna juice about half of a lemon. So I'm gonna take the lemon, cut it in half, and juice half a lemon. It's about an ounce. I'm just gonna put it straight in here since it's easier than putting it into my small little measuring cup. Okay, and we'll give this just a little stir again. Get it all nice. Okay, and now 2 ice cubes in each. One, 2, 1, and 2. As you can see, they're getting pretty full. And so now the final thing in each one is going to be the dark liquid that'll sink to the bottom, give that sunrise kind of effect. So in the one with orange juice, that was drink number 1, where you're just going to add about half an ounce of grenadine. Again, I'm just going to eyeball it. That looks good. And this part's maybe a little tricky. I'm still not great at it, but you want to sort of pour it slowly down the side of the glass so it sinks to the bottom, hopefully gets a little bit of gradient, but we'll see. So it kind of just sinks to the bottom. Yeah, red on the bottom, orange on the top. And then in this other one that had the lemon, we're going to do similarly, sort of a combination of the grenadine and the creme de cassis, which is a black currant liqueur.
Yeah, it happened again. All right, well, we'll stare at Arvin Gupta's face for a few seconds here while we wait for Jacob to come back. All right, here he comes again.
He's back.
Hey,
So the a little less than half an ounce of the creme de cassis, and just a little more than that of the grenadine. So in total, just about 1 ounce, about evenly split, but I favor the grenadine just for color. I think I like the flavor of the creme de cassis better, but for color effect, we'll go. Again, we'll pour it down the side here so that it hopefully goes to the bottom, but this one's a bit of a darker color. And the liquid in it with the lemon juice isn't quite as opaque as the other drink. So the gradients, maybe not quite the same. But here we have 2 little binary sunsets. And I'm going to very quickly just garnish with a slice of lemon. And I have a clementine. If you have an orange, you could use an orange. Sorry that it wasn't on the ingredient list, but for aesthetics, we'll go ahead and garnish these bad boys. Stay. And there you have it, binary sunset. I'm not going to lift these because they'll go everywhere, but binary sunset, again, you get this gradient effect, the nice sunset, but I prefer to just stir it up and drink it because then all the flavors combine and you don't get all the grenadine at the end, which isn't very pleasant. So take your pictures, tweet them at us. Hopefully they turned out well. Sorry about my robot voice. I'm going to hand it back to Michael. Cheers to you all. Cheers.
Thank you very much. We managed to get through it. Let's cross our fingers and hope that we manage to actually stay online for the rest of this show. I'm kind of worried about me accidentally disconnecting something. All right. Well, let's go ahead and get started with the science part of Astronomy on Tap. So our first speaker of the night, as mentioned before, from Penn State, Dr. Carmen Carmona is going to tell us all about how we are detecting dark matter directly. So go ahead, Dr. Carmona, take it away.
Can you see my screen?
Yep, looks good.
Okay, great. Well, I'm Carmen Carmona. I'm a professor at Penn State University. First, I wanted to thank the team from Astronomy on a Tap for inviting me to be here today to talk to you about dark matter and how we are searching for it 1 mile underground. Here, you can see a pie chart of the composition of the universe. And you see how ordinary matter, everyday stuff like atoms, planets, stars, that's only 5% of the universe, while the other 95% is a mystery. 68% is dark energy, but I'm not going to address that in this talk. I guess we'll hear that in the next talk. And I'm going to talk about this other 27% of the universe that is dark matter. So if we look at the fraction of matter in the universe, if we look at the matter, the dark matter makes up 85% of the matter of the universe. And you can think about this. Imagine, for example, that the scientists have been, for the past 200 years, have been looking at an animal. We think we know everything about it. We know how it behaves, we know the parts, the physiology. And just in the last couple of decades, we discovered that all this time, we've been looking just at the tail of a giant animal, of an elephant. So that is more or less the situation that we have in physics today, in which we realize that all this time we've been just looking at a tiny, tiny bit of the universe. And we want to know now, what is this dark matter, this 27% of the universe? How did we find ourselves into this situation? Well, we found plenty of evidence pointing towards the system of dark matter, of this missing matter of the universe. And it was first proposed by Fritz Zwicky in the 1933 by looking at the coma cluster. But it was taken more seriously in the 70s with the measurement of the rotational curve of the galaxies. And since then, we've been gathering more and more evidence towards the existence of this missing matter of the universe. We have evidence from cosmology, from the cosmic microwave background and the larger structure of the universe. And we also have evidence from gravitational lensing. But today I'm gonna focus on one of the most compelling pieces of evidence, that is the rotational curve of galaxies. And in fact, these measurements were first done by a Pennsylvanian, by the astronomer Vera Rubin in the 70s. So at that time, they look at the galaxies, and when you look at the galaxies, most of the visible matter is at the center. So then you think, okay, so if most of the matter is at the center, and now we have stuff orbiting around the center of the galaxy, like stars. So if we look at the star that is far from the center, it's gonna move slower than a star that is closer to the center. So that is what they were expecting to measure. So if we look now at this plot on the top, and the zero is at the center of the galaxy, as we move far from the center, they were expecting to measure something like these dashed lines, so that the velocity will be falling down, it will be decreasing as you go far from the center. However, what they actually measured was this other curve on the top. And as you move farther from the center of the galaxy, these stars that are far, they still move at the same velocity than the stars that are closer to the center. So how is this possible? So in order to explain that, that means that you need to have a large amount of matter that is not visible in the galaxy. And it's what we call the halo of dark matter that is in this picture on the bottom, is colored in blue. So we have dark matter in all the galaxies. We also have dark matter in our galaxy, in the Milky Way. And here I can show you a simulation of the galaxies. The one on the left has dark matter and is shown in pink, and the one on the right is a simulation with no dark matter. So this is going to show you how it works. So if you look at the one on the left, you can see how the stars from the center are moving fast as the one closer to the center. However, if you look at the galaxy on the right, then you see how these stars are moving that are far from the center and moving slower than the star closer to the center. So again, this is what they were expecting to measure, the stuff on the right. But what they actually measure and what we can measure today is the curve from the left. So we do have dark matter in the galaxies. And what do we know about dark matter? Well, we know that this matter interacts gravitationally with the universe and occurs in clusters. We know that it's dark. That means that it doesn't emit or absorb or reflect light. So it's invisible, it's impossible to see. And it's not baryonic matter, it's not made of protons or neutrons. We also know that dark matter is everywhere. In fact, you have now plenty of particles of dark matter passing through you. You just don't notice it. And what else do we know? Well, that is pretty much it. That's all we know. So we have many theoretical models and candidates for dark matter, but we haven't been able to detect a dark matter particle yet. So the search goes on. And you can think, well, could dark matter be just normal matter, but that we cannot see, like neutron stars or black holes? Well, we have looked at all these objects in the past decade, and they exist, but even if you combine all of them together, they cannot even reach 5% of the missing matter in the universe. So they are not enough. So they need to be something else. So we have many candidates for dark matter. We have many theories. And here you can see how we have the candidates for dark matter had a very wide range of masses. Astrophysicists, we like measuring mass in electron volts instead of pounds or kilograms. So to give you an idea, here you have this blue dot, it's an electron, and this other one is a proton. So some of the dark matter candidates are very light, much smaller than the electron. And some of the candidates can be very heavy, much bigger than protons. But from all of these, the most popular candidate is the weakly interactive massive particles, or WIMPs. They have a mass range between 1 to 2,000 of GeV, of gig electron volts. And we call it massive because they are massive related to other particles, but not relative to everyday objects. So in fact, they can weigh just a little bit more than a proton, 200 or 1,000 of times more than a proton. And we say that they are weakly interacting particles. What we mean by that is that they rarely interact with other dark matter particles or with normal matter. So that is going to make it very, very difficult to detect. So then how do you detect something that is invisible? Well, think of yourself in a dark room. How do you know, for example, that there is a table? Because you bump into it, right? So we are trying to do the same with the direct detection of dark matter. We are looking for this interaction of dark matter particles with normal matter. And in particular, we are expecting that these WIMPs are gonna collide, are gonna interact with the nucleus of the atoms, or they are gonna produce a nuclear recoil. And as I said, this is very rare. It happens at a very low rate. We expect to have less than 1 event per ton of material per year. And we have challenges. We have many backgrounds. We have many particles that are also going to interact with our detectors, like gammas or electrons or neutrons. All these particles are coming from cosmic rays from out of space and from natural radioactivity in the environment and radioactivity in the detector materials. So looking for WIMPs is like looking for a needle in the haystack. And what is the best way to find the needle? Well, you get rid of all the hay, right? So can we blow away the hay to find the WIMP? In order to do that, then we need to reduce all these backgrounds. The backgrounds that we have at a high rate, we have many, many background events. So how can we reduce them? We have a few tricks. The first one, we can go deep underground. So our detectors are going to be in underground laboratories that help us to shield against cosmic backgrounds that come from out of space. Imagine, for example, that you are at sea level and you open your hand. Then you are going to have about 1 million passing through your hand per second. Now you go underground, you go 1 mile underground, and then you open your hand. Now you're going to have 1 million passing through your hand per month. So you really reduce the amount of backgrounds by going underground. And that is what we do. We have all this earth between the surface and the lab and the ground to shield against these cosmic rays. What else can we do? We can also surround our detector with a shielding material, with a veto system. Different materials that we can use for that. We can use lead, we can use scintillator, we can use water, tons of water, a very big water tank, and then put our detector inside. That is what you see here. And that helps us to shield against all the external backgrounds and not letting these external particles to reach the inner part of the detector. Is there anything else that we can do? There is one more thing, and it's that I told you that WIMPs are expected to scatter the nucleus of the atom. But most of the backgrounds that we have, like electrons and gammas, they are going to interact with the electrons of the atom. So they produce electron recoils. And it happens that in our detector, we know how to discriminate, how to differentiate between these nuclear recoils and electron recoils. So we can get rid of most of the backgrounds. And using all this technique, we are trying to find the needle in the haystack. We are trying to find WIMPs, dark matter particles. I work in one of the largest dark matter experiments, LC. It comes from the joint of the LAX and Zeppelin collaboration. We have 34 institutions with about 250 people. We have institutions from all over the US that you can see here in blue, several of the national labs as well. We have institutions from the UK. We also have collaborators from Portugal and from South Korea. This is a picture of our latest collaboration meeting that, of course, nowadays is online. And we need to have our detector underground in order to shield against cosmic rays. So we are located at the Sanford Underground Research Facility, SERF. This is in Lead, in South Dakota. It was a former gold mine, and after they were done extracting the gold, they donated to science, homestake. If you've been in South Dakota, it is very close to the Mount Rushmore. And if you have seen the TV show Deadwood, Deadwood is the town next to Lead. This Sanford lab is one of the deepest labs in the world. We are operating our detector 1 mile underground. So there is where we have the LAX detector that was the predecessor to LC. And now we have the LC detector. And again, this is going to help us to really shield our experiments against the cosmic rays. So to go on the ground, we need to dress like miners. We take these elevators with no lights. It takes us about 10 minutes to go 1 mile on the ground. I learned how to drive the train on the ground as part of the guide training. That was fun. And this is a picture 1 mile on the ground. You can see here the door to the cage, and these other corridors is the one that go to the lab. So here you can see a drawing of the RC experiment. What you see here is a very big water tank, and the detector itself is at the center. We use liquid xenon in our experiment. So the normal matter that we use is xenon. We are looking for interaction of dark matter particle with the xenon. And we have a lot of xenon. We have 10 tons of xenon. RC is gonna be the largest experiment, dark matter experiment to date. So let me show how we look for particles. So I'm gonna zoom in at the center of the detector. And on the bottom, we have liquid xenon, and on the top, we have gas xenon. So when a particle interacts with the xenon, produces light and electrons. We drift these electrons towards the top of the detector, and then they produce a secondary light. And we see these two flashes of light with photo detector that we have on top and bottom of the detector. We have about 500 of them, and they are able to detect single photons. So we are looking for this signal from dark matter. And if we don't use shielding, if we don't go on the ground, this is how noisy, how much backgrounds we have in our detector from cosmic rays, from radioactivity. So it's very, very difficult to look for dark matter. So what do? As I explained, we are gonna shield our detector against these backgrounds. So the first thing that we do is that, in fact, we use the 80% of the xenon that is at the center of the detector, and we use the other xenon as a shielding already against backgrounds. And then we are gonna keep putting layers. So we have a layer of liquid xenon around that is used to reject neutrons and gammas. And then all that is inside 2 cryostats that are made of low radioactive titanium. And there is a vacuum in between them. And those cryostats are surrounded by a liquid scintillator. And here you can see that in green and in blue on top and bottom and around the detector. So that is going to help us to shield against gammas and neutron backgrounds. And all this is in a very big water tank. It has 70,000 gallons of water, so it's really large. So all the external backgrounds are going to be stopped before they reach the detector. And all this is happening 1 mile underground so that we can shield against these cosmic rays. So we spent the past few years building the detector. And here you can see some picture of the actual thing. So this is the most inner part of the detector from the outside, and here from the inside, a top view. So what you see here on the bottom are these photo detectors that we use to detect light. We have about 250 here on the bottom, and we have an array on the top with another 250. You can see this is very wide. That is because we cover everything with Teflon. It turns out that Teflon has a very high reflectivity. So that is going to help us to make sure that we can detect as much light as possible. And we assemble all this at the surface inside a clean room. And then we put this inside one of the cryostats, and we bring it on the ground. The detector doesn't fit inside the cage. So here you can see it hanging on top of the shaft, and then we brought it down. And in this picture on the bottom center, you can see already the detector inside the lab underground. Here are a few more pictures on the ground. You can see now we continue building now all the shielding around the detector. This is inside the water tank, and this picture is the outside of the water tank. You can see it's really big. It's 26 feet diameter by 20 feet height. And in this picture, you can see the cryostat, the detector itself is at the center. And then we have these acrylic tanks that are going to be filled with a liquid scintillator. And then we have the water tank that is filled with water. So the construction of the experiment is almost done, and we are expecting to have results already this year in 2021. So it's very exciting times for us right now for direct detection of dark matter. So in conclusion, dark matter makes up 85% of the matter of the universe, and we know about it from its gravitational effect, but we still haven't been able to detect these dark matter particles. Dark matter is everywhere, so that means we can use a very sensitive detector here in Earth, like LC, to search for dark matter particles. But we are going to have to fight against backgrounds. We have plenty of backgrounds that are also going to hit our detector, like cosmic rays and radioactivity. So we need to go deep underground and use layers of shielding around our detector. And the first results from LC experiment are expected this year in 2021. So stay tuned. Thank you.
Awesome. Thank you very much for giving that talk. Oh, I just turned your video off. I apologize for that. Oh shoot. Everything is just going haywire today, isn't it, man? All right, we're back. So if you do have questions for our speaker, please go ahead and type them into the YouTube chat. So we've got one question already. Why was xenon selected for the experiment?
Well, xenon is an ideal candidate. One of the advantages that it has is that it's very dense. So that means that it's going to prevent external backgrounds from penetrating deep inside. So already help us as a shielding, self-shielding of the detector. It has also some advantages because some of the candidates that we look for, like the WIMP, spin-independent WIMP dark matter, are going to have a dependence with the A square, with the atomic mass. And xenon is heavy, so that means that it's also going to help us on this type of searches. Also, it's very easy to escalate to bigger sizes. So in fact, when we started doing the first detector, we only have like a few kilograms of xenon. And now we are at the multi-ton size of detectors. So we've been able to escalate easily xenon. It has some other advantages that xenon itself is very clean. It doesn't have isotopes that last a long time. And that is important because other material, like for example, argon that is also used, has argon-39, an isotope that is one of your backgrounds. So xenon doesn't have any of those isotope itself that will be a background for our searches. So it's very good as a target.
Okay. What do you fill that tank with water? Is it just like regular tap water? Is it like heavy water, or is it
deionized water?
Okay.
It's just very clean water.
Okay. Would there be any advantage to freezing it and having it as ice as opposed to liquid water? Would that provide any extra protection? Or?
No, in fact, water is already very good at stopping anything, and it's very large. So it's 300 tons of water what you have inside. So if you think about any particle trying to go from the exterior, it's always gonna be. It's like you have 26 feet, and the detector is inside. The detector is about 1.5 meters diameter. So you have so much water that any particle from the outside is not gonna get into the detector. But our system, in fact, our shielding is more complex than just water. So we have the scintillator that help us not just with external backgrounds, but with backgrounds from radioactivity in the materials from the detector. So those ones are more tricky. And this liquid scintillator is going to help us to tag some of these backgrounds.
Okay. So we got another question here. Any guesses as to why dark matter isn't mostly in the center of galaxies like regular matter? So I guess asking about the distribution of
well,
dark matter.
if I showed you, if you remember this rotational curve of the galaxies, if it was all at the center, right? If all the matter is at the center, as you go farther from the center, then the gravitational pull, it should be smaller. And that is why the velocity should fall. But what you see is that the velocity, it remains flat, kind of flat, as you go far from the center. So that is why we know that this dark matter is not just at the center, it's also around the galaxy. It has to be farther from the center as well. So it's this halo of dark matter that we have around.
Okay. So another question here. Do you have to deal with a bends or nitrogen sickness when you go down 1 mile underground? Like, is there
Sorry,
any
say that again, if I have to deal with?
with the bends or nitrogen sickness? So is it like when you go deep sea diving, divers have to, you know, do these depressurization steps, I guess, because you get nitrogen bubbles in your bloodstream. Do
No,
you not
we
have that
don't.
pressure? Okay, yeah.
No, we don't have that issue.
That's right. So I know as you go into the Earth, you do run into nuclear material that is in the crust, like potassium, uranium, just kind of naturally occurring elements. So two things, I guess. One, I've heard that as you go further into the Earth, it gets really warm because of that. So was it like really hot in the mines?
Well,
And
it is. We have air conditioning. It's
okay,
refrigerated, but you can notice you can notice sometimes that where it gets warm. So when we get ready to go inside, we have some of this air coming out, and then you can notice that it used to be warm. But in fact, inside the mine, when you are underground, at least in the level where we have the lab on this 48, 50 feet level, we do have a very big ventilation system, a very good one. So in fact, it's kind of cool. It's kind of cold on the ground. But I know because I've been doing some walk around and as a guide, and heard from talking to some staff that work at the mines. And if you go to some other levels, yes, it can be very hot, or very warm there.
okay. Do you get any extra contamination, any extra contaminant signals from that nuclear material as it decays? Like, would it is it
Well,
more
you may think,
beneficial?
for example, underground, you have more radon, or you may have more radon, right?
Mhm.
But as I told you, we have these very big water tanks. So anything that is
Okay.
outside on the wall of the mines is not going to reach the detector. So in fact, what we worry the most is with the component of the detector itself. So this titanium, for example, that we use to build the cryostat, we do have a lot of research and R&D to make sure that we find very low radioactive titanium. And then any screw, any nut, anything that we put inside, we screen for radiation. So nothing goes inside the detector without being screened for radiation. So to make sure that we are going to have very low backgrounds.
Okay. What would a non-detection tell us about dark matter if you aren't able to detect any signals from WIMPs?
Well, it is still important because it will help us to put constraints in theoretical model that we have right now. So it wouldn't tell us what it is, but it will tell us what is not. And okay, it's not on this side, so you put some constraint to that model.
Okay.
And in fact, with LC, we are not model dependent. So we do the only requirement that we have is dark matter need to interact with normal matter, with xenon. But other than that, we are not model dependent. So we can look for different candidates for dark matter.
Okay. And then another follow-up onto a previous question about the dark matter distribution. Um, we're asking, I guess, about the dark matter in the halo of the galaxy, in the center of the galaxy. What do we know why the dark matter distribution in galaxies is the way that it is? Do we have an idea for why there is dark matter in the halo?
Well, there is many theories to trying to explain, but the main thing is we have observational measurements. So from cosmology and astrophysics, and not just the rotational curve of the galaxies, we also have, I didn't have time to explain all the evidence, but there is gravitational lensing also helps you to map where is this dark matter. So gravitational lensing can help you identify cluster of dark matter. Because the light will bend if it passes close to a big mass, right? So you cannot see it, but it's going to bend the light. So it's going to create, for example, several images of a galaxy that is on the other side of the cluster of dark matter. So all that helps you to have an idea of the location of this of dark matter. But it's basically through observational proof that we have.
Okay. And there are, I'm assuming that there are other detection facilities out there that are also trying to look at this. Are they all using kind of similar methods of trying to, put something deep underground, isolate it, and look for these kind of interactions? Are there any other ways that we could try to look for dark matter?
Well, there are plenty of things we can do. And in fact, there are many, many groups trying to look for dark matter. So what I was talking about, Elsie, is a direct detection experiment. And in fact, there is other type of direct detection experiment. It doesn't need to be just with xenon. We can use for example, germanium or silicon detector or argon. There are some other technologies that we can use. And also, but that is for direct detection. We can also look for dark matter, not here in Earth, but out in space. We can look for annihilation of dark matter particles, and that is what we call indirect detection. And then there is something else that we can do that is in colliders, like the look for production. So dark matter, two standard model particles colliding and producing dark matter. So there are different ways that we can look for that. Some of them are model dependent, like the one that you do in colliders. The good thing about direct detection is that we on some of the experiments, like the one that we use in LC, we are not model dependent.
Okay. Well, very cool. Thank you very much for coming out and taking the time to give a talk for us. Really appreciate you coming out here. Thank you.
My pleasure. Thank you for the invitation. Bye.
Bye. All right, we are going to go ahead and start our trivia. And I have the link, which I am going to paste into the chat. So if you want to play trivia, go ahead and follow that link, and Arvin will take you through this week's trivia.
Cool, thanks, Michael. Can you see my screen?
Yep, you're good.
Great. All right. So as Michael said, the link to the trivia should be in the YouTube chat. It's also at the bottom of the slide here in case you can't see the chat for some reason. So the way this works for those who are tuning in for the first time, or for those who need a reminder of the instructions, is every month when we have Astronomy on Tap, we have a round of themed trivia. So this month's theme is Women in Astronomy. I'm going to ask you a series of 15 questions, all of which are related at least tangentially to the topic, which is Women in Astronomy tonight. And you will submit your answers through that trivia link that's right here. I will grade everybody's answers, and at the end of trivia, I will choose a winner based on whoever has the highest score out of 15 points. In the event that there is a tie, I will do a tiebreaker based on which team has the best astronomy themed team name. So in that answer form, there is a question where it asks you for your team name. If you think you're doing well, or if you think you have a shot at winning, try to come up with something nice, creative, and astronomy themed to get that tiebreaker. So, also the winning team will get some nice prizes. We have magnets, beer koozies, masks, courtesy of our friend Macy Houston, and also bottle openers from the Central Pennsylvania Observers. So if you want one or two of these prizes, we will send them your way if you manage to win tonight's trivia. To start out, I'll do a quick example question so that you all know how this is going to work. And for the first example tonight, the question is, Caroline Herschel contributed to the discovery of which planet in the 18th century? And the correct answer, as many of you hopefully know, is Uranus. So Caroline Herschel and her brother William Herschel both helped to discover Uranus back in the 18th century. So without further ado, let's move on to question number one. So number one, Ellie Arroway, the main character of Carl Sagan's novel Contact, was inspired by which astronomer? And it's one of these four. It's either Jill Tarter, Jocelyn Bell Burnell, Annie Jump Cannon, or Carolyn Shoemaker. I'll go through all of these again at the end, but for now I'm just gonna run on through. Number two, With the upcoming blank program missions, NASA aims to send the first woman to the moon. And the goal here is to fill in the blank with one of these options. Is it the Hera program, Aphrodite program, Artemis program, or Nemesis program? Number 3, what is the diameter of the primary mirror of the Nancy Grace Roman Space Telescope? This is a space telescope. It was formerly known as W-FIRST. It's planned to launch sometime between 2021 and 2030. And it's named after Nancy Grace Roman, who was NASA's first chief scientist. And also for number 3, I will accept any answers that are within half a meter of the actual diameter of the mirror. Number 4, Carolyn Porco directed, there's an extra word in there. Carolyn Porco directed Cassini to capture this photo of Saturn and Earth, which is titled, is it Pale Blue Dot, Earthrise, The Blue Marble, or The Day the Earth Smiled? And it is kind of hard to tell, but this is Saturn here. And then right below these rings, that little blue speck right there, that's Earth. A really, really high quality, high resolution version of this photo is available online, and you can actually make out a little better that that really is Earth there and not just a speck. Number 5, the Leavitt law, named after Henrietta Swan Leavitt, relates which 2 properties of Cepheid stars? Is it their surface temperatures and helium abundances, pulsation periods and absolute brightnesses, magnetic field strengths and rotation periods, or their age and the number of planets in their systems? Number 6, which astronomer discovered that stars are composed primarily of hydrogen and helium? Was it Valentina Tereshkova, Henrietta Swope, Annie Jumpcannon, or Cecilia Payne-Gaposchkin? Sorry, I can't pronounce that one. Number 7, which astronomer was awarded a share of the Nobel Prize in Physics in 2020? Was it Andrea Ghez, Jocelyn Bell Burnell, Marie Curie, or Mae Jemison? Number 8, the 4th century philosopher Hypatia made several contributions to astronomy, including edits to the book Blank by Ptolemy. This is an incredibly famous work in early 80s astronomy, so it's not an obscure question by any means, or it shouldn't be at least. Number 9, the comet Shoemaker-Levy 9, named after co-discoverers Carolyn Shoemaker and David Levy, collided with which solar system planet? And this is a shot of a lot of the fragments of the comet prior to their collision. Number 10, NASA's headquarters in Washington, D.C. is named after which Apollo-era engineer? Was it Margaret Hamilton, Mary Jackson, Katherine Johnson, or Nancy Grace Roman? And it was named this only recently, I'd say a year or 2 ago at most. Number 11, while studying galaxy rotation curves, Vera Rubin found observational evidence for blank: gravitational waves, the cosmic microwave background, dark energy, or dark matter. Number 12, which astronomer designed the canonical OBAFGKM system of spectral types by which stars are classified? Was it Annie Jumpcannon, Cecilia Payne-Gaposchkin, Katherine Johnson, or Caroline Herschel? Number 13, Jocelyn Bell Burnell discovered which type of star? T Tauri stars, cataclysmic variables, pulsars, or blue stragglers? Number 14, who was the first woman to go to space? It is this woman pictured here. I tried to choose an image that wouldn't give away too much else about her, though. Number 15, astronomer Andrea Ghez discovered that there is a blank at the center of the Milky Way galaxy. Fill in the blank. All right, so we do ask that you submit your answers before the end of Astronomy in the News, which is the next segment, because I'm going to try to start grading them after that and be quickly done before the end of the second talk, so that we can share the results of the trivia and who the winner was after the second talk. But first, I will take a minute to quickly go through all of these questions again so you can see them. Number one, Ellie Arroway, the main character of Contact, was inspired by which astronomer? Number two, with the upcoming Planck program missions, NASA aims to send the first woman to the moon. Number three, what is the diameter of the primary mirror of the Nancy Grace Roman Space Telescope? And all of these questions should also be in the trivia form that you have. So if you don't catch them here, just take a look there. Number four, Carolyn Porco directed Cassini to capture this photo of Saturn and Earth, which is titled blank. Number five, the Leavitt law, named after Henrietta Swan Leavitt, relates which two properties of Cepheid stars? Six, which astronomer discovered that stars are composed primarily of hydrogen and helium? Number seven, which astronomer was awarded a share of the Nobel Prize in Physics in 2020? Number eight, the 4th century philosopher Hypatia made several contributions to astronomy, including edits to the book Planck by Ptolemy. Number nine, the comet Shoemaker-Levy 9, named after co-discoverers Carolyn Shoemaker and David Levy, collided with which solar system planet? Number 10, NASA's headquarters in Washington, D.C. is named after which Apollo-era engineer? Number 11, while studying galaxy rotation curves, Vera Rubin found observational evidence for blank. Number 12, which astronomer designed the canonical OBAF-GKM system of spectral types by which stars are classified? Number 13, Jocelyn Bell Burnell discovered which type of star? 14, who was the first woman to go to space? And number 15, astronomer Andrea Ghez discovered that there is a blank at the center of the Milky Way galaxy. Again, submit before the end of Astronomy in the News, and good luck to everybody. With that, I will hand it off to Brianna for Astronomy in the News.
Awesome. Thanks, Arvind. Great. So welcome back to another month of Astronomy in the News. Today, I'm going to give you a few updates from NASA's Perseverance rover and also talk briefly about telescope pirates. So I'll start off with a quick recap from last month. Those of you who tuned in last month may remember that NASA's Perseverance rover safely landed on Mars on February 18th, as well as a few other Mars missions that successfully made it there. So a lot has happened in the last month. Perseverance, or Percy for short, has been active on Twitter, letting us know what's been going on. Once the mission successfully landed, we're not quite out of the woods yet. There's still a lot of tests that we need to do before we can get to doing good science with the rover. So on March 4th, Perseverance tweeted that they were doing a quick test of its steering. So at this point, they were basically testing instruments. They tested the Perseverance robotic arm motion. The arm is pretty complicated and can move in a variety of ways. So we need to make sure that it can move in all the ways it's expected to move in, so that it can carry out its full range of motion. Perseverance also tested its image taking abilities and has sent us some great images so far. And just like in the tweet says, tested its steering. Oops. Okay. Perseverance also took a little test drive, saying, "I'm on the move, just took my first test drive on Mars, covering about 16 feet or 5 meters. In the picture there, you can see its little wheel tracks as it's driving around on Mars. And again, it took a great picture for us to see that. March 8th, Perseverance says that it's continuing to scout a spot where it will drop off the Mars helicopter. So I haven't talked about the Mars helicopter, even for those of you who were listening last month. I didn't mention the helicopter, but there is a little helicopter attached to the bottom of Perseverance. It's named Ingenuity, And I'll talk more about that in a moment, but you can see it on the right there in the red circle, just sort of hanging on. And this is with the dust cover off. Percy also launched its music career, saying things are sounding really good here. Listen to the first sounds of wind captured by my SuperCam microphone. If you're interested, or if you're a little bit tired of listening to the top 40, you can head over to NASA's SoundCloud and listen to some audio recordings from Perseverance, including audio recordings of wind or Perseverance shooting some lasers, which will help us identify the composition of rocks, I believe, and also audio recordings of Perseverance driving around. So if you need a change of pace in your music, you can feel free to check that out. On March 17th, Perseverance tweeted that it is checking out the tools for one of its key goals, to collect and store samples that a future mission can bring back to Earth. So Perseverance is, or over the past week, has been testing its sample collection mechanism. So these samples are going to return to Earth one day. That's the first time we've done something like that. So it's a really novel feature of Perseverance. So it's great that that's being tested out. Hopefully everything has gone perfectly in that regard. A little bit more on the Mars helicopter. Just yesterday, Perseverance dropped the debris shield that was protecting the helicopter Ingenuity. It's still all folded up and tucked nicely underneath Perseverance. And in a few days, Perseverance will have driven to the designated helipad, which is the location that was deemed suitable for Ingenuity to do some test runs. Ingenuity is expected to take flight in April of this year. It's basically our first space helicopter. So it's mostly a tech demo rather than something that has a big science goal, but it's really exciting because it is, again, our first space helicopter. I don't know if I said telescope or helicopter a minute ago, but it's our first space helicopter. And that's a novel thing because it's a lot different to fly a helicopter on Earth versus Mars because the atmospheres are completely different. So that's about it for Perseverance. Now I'm going to talk a little bit about the concept of pirates and the James Webb Space Telescope. You may have seen a little bit of discourse about this over the past month or two. I think most of it was spawned by this tweet from Christopher Consulis that said, learned today that the exact day when JWST will be shipped via boat to its launch site is a secret, as there are fears of pirates capturing it for ransom, just when he thought things couldn't get worse. Things couldn't get worse, of course, referring to the many delays JWST has endured, in addition to going over budget and having to finish up everything during COVID. And this also spawned an article from The Atlantic, Who Would Kidnap a Space Telescope? And this article kind of just went through, again, summarizing some of the problems that JWST has experienced in its development, and also provided an interesting tour through astronomy history and cited some examples of other telescopes or telescope parts getting held for ransom. And all of this also spawned a flash game, which I found pretty entertaining. The idea is that you get James Webb to go from its current location in California all the way to its launch site in French Guiana without being attacked by any of these little pirates, which are also moving around the screen. So if you go to this link, you can play this game and see if you can successfully get JWST to French Guiana without getting captured by the pirates. It's really easy. You just use your arrow keys, move around, and do your best not to get captured. So it was a fun little distraction for a few minutes. That's all I have for Astronomy in the News this month. Hope to see you next month.
All right, thank you, Brianna. So unfortunately, our next speaker doesn't seem to be here. So I'm going to give you a very impromptu talk about the cosmic tension, the crisis in cosmology. So what we had wanted to talk about was how we're trying to determine the Hubble constant and how our different measurements seem to disagree with each other. And this has been going on for a long enough time now that this seems to actually be something of a problem. So I am going to try to share my screen while actually streaming, and I have no idea if this is going to work. So give me 1 second. Okay, I think you can see this. You can see it well enough. Not exactly the best presentation, but you know what? Whatever. It's one of those. It's one of those nights. Okay, so the Hubble constant is important because that will kind of tell us how fast the universe is expanding, and in that sense, will also tell us the age of the universe. And so this was first kind of determined back in the 1920s by Edwin Hubble, and it was really important because it allowed us to figure out that the universe is expanding, not just that it's expanding, but it helped solve the question of, are those galaxies that we see in the sky actually galaxies, or are they in our own galaxy? So Hubble was able to determine the distance scale using something called Cepheid variables. And so these stars are pulsating stars. They have a pulsation period, which is tied to their luminosity. So if you can measure the period of a Cepheid variable,
Michael, I think we're not
yes.
seeing your screen.
Oh, shoot, figures. Well, you know what? That's just how it's going to be, I guess. All right. Can you see me? Can you see anything at all?
We see your lovely desktop background.
Oh, nice. What about now? Can you see anything now? My screen sharing is paused. Why is my screen sharing paused? How about now? Can you see anything?
Unfortunately, not yet. The YouTube stream is like it lags
Oh,
like
yeah,
10
I can see
seconds
it
behind
now.
us.
Let me see. There we go. Now it's popping up. Okay,
Beautiful.
awesome. And there's me. All right, so this plot that I was showing you then, that I was trying to show you, is the evolution of the Hubble constant over time. So we've gotten better with our measurements, and we've been able to narrow down the Hubble constant at better resolution as time has gone on, as we've gotten better telescopes. So we've really gone a long way since the 1920s. You can see how this is kind of sloping back down. Uh, it appears that you're converging to a single answer, but when you get really close into the nitty-gritty here, you see something more like this, where there does appear to be a bit of a divergence. So there's multiple ways that you can measure the Hubble constant. The way that we've done it for a while, that Hubble did, is he would look at these Cepheid variables. You look at them in a galaxy that's really far away. You measure the redshift of that galaxy, so how far is that galaxy moving away from you? And then you find out how far away it actually is using these Cepheid variables. So that will tell you that a galaxy that's, 100 megaparsecs away is moving at a rate of so many kilometers per second per megaparsec. And that allows you then to determine this value, to determine the Hubble constant. Kind of the more recent way to do it is that you can use the CMB background, the cosmic microwave background, and you can try to fit a data model to the cosmic microwave background using parameters like the composition of the universe, the how much dark energy there is, how much matter there is, how much light radiation there is. And doing that will also give you a separate value. So the Cepheids and the cosmic microwave background are different from each other. They are measuring the same thing but differently. And you can see that in around 2008 to 2012, these values started to diverge. So the values that the Cepheids are getting are around 71 to 73 kilometers per second per megaparsec, whereas the CMB is around 68 kilometers per second per megaparsec. And that doesn't sound like much, but the important thing is that we're able to do this with a finite enough resolution that the error bars don't overlap. So these do seem to be different numbers. So kind of the big question is, can you measure H naught, the Hubble constant, independent from Cepheids and independent from the cosmic microwave background to get some other third dimension in here? And so one way to do that is to use, it's called the TRGB, or the tip of the red giant branch. Stars at the tip of the red giant branch, this is a stage in their evolution, are at a relatively constant luminosity. So if you can measure that, if you can measure the tip of the red giant branch in faraway galaxies, that gives you another distance indicator. And just like you did with the Cepheids, you measure the distance to this galaxy, you measure its spectrum, you get its redshift, you know how fast it's moving away from you. And so doing that, then you can tie the redshift to the distance, determine H naught. And of course, this one lands kind of right in the middle. It's around 69 kilometers per second per megaparsec. So it's kind of confusing things a little bit more. Multiple other ways to do this, again, to find distance. You can look at lensed quasars. Those will give you another measurement which is independent from Cepheids, the red giant branch, or the CMB. And if you look at that lensing pattern, then you can determine H naughts independent from those, and they happen to line up more with the Cepheids. You can use the fluctuations of an elliptical galaxy. So elliptical galaxies are generally pretty smooth as you go from their centers outward. If you look for fluctuations in that surface brightness, well, the closer a galaxy is to you, the more fluctuations you'll see, just because you can resolve these little tiny patches of stars better. Faraway galaxies won't have as many fluctuations, so they'll appear smoother. You can use that to determine distance. That method happens to agree more with the Cepheids. The cosmic microwave background measurements that we have here have been done from the Planck and the WMAP telescopes. So those are space telescopes which have looked at the cosmic microwave background. If you do the same measurements here on Earth, looking at the cosmic microwave background again, but from telescopes on the Earth, they line up more with their original cosmic microwave background measurements. So this is what we mean when we talk about the crisis in cosmology, or the tension over the Hubble constant. Diverging answers, which, again, not too long ago weren't, that looked pretty good. It seemed like everything was coming together. But then things start drifting apart just a little bit, and it seems that maybe we do need to start looking at the physics of it. Is our physical model of lambda CDM, cold dark matter, dark energy, some constant dark energy model of the universe, is that accurate? Is that reflective of our true universe, or do we have to tweak something? So there was a paper that came out a few months ago that looked at they're tweaking the energy density of dark energy, and I think they were saying that it was either increasing or decreasing from the beginning of the universe to now. I can't remember which, but essentially the energy content or the energy density of dark energy shifted, and it changed. And when they ran that through their model, they got something that was closer to 71 kilometers per second per megaparsec. So perhaps we do need to look more at the physics of our physical models that are going into CMB. Maybe we do need more measurements. You always need more measurements in astronomy. Why not get more funding? We're not really sure. That is a very slapdash overview of the Hubble constant. If you do have questions, you can type them in the chat. I can try to answer. Can't really guarantee that I will be able to solve anything, but we wanted you to have something and not just stare at us or leave early. So something to listen to. So, are there any questions? No, I don't think so, but that's okay. I hope you learned something. I hope I made sense somewhat. You can really, if you want to learn more, you can Google like Hubble tension or cosmological crisis, and there's going to be a ton of articles that you could read for that. All right, this has been a very adventurous night for Astronomy on Tap State College. We are going to go ahead and, yes, Arvin is back to give us answers to trivia. So go ahead, Arvin.
Thanks, Michael. I don't think Einstein could have said it better himself about dark energy. So good job. That was very well done, all things considered. Yeah, so we're going to go ahead and go through the trivia answers here. So thank you to everybody that played and attempted and submitted things. So prizes, again, this is a reminder of what's on the line for you all. Number 1, Ellie Arroway, the main character of Carl Sagan's Contact, was inspired by which astronomer? That would be Jill Tarter. Carl Sagan has said that he did base Ellie Arroway in part on Jill Tarter, who is a real live scientist and a very, very accomplished, very successful woman in the field of SETI, so the search for extraterrestrial intelligence. Number 2, with the upcoming blank program missions, NASA aims to send the first woman to the moon. The correct answer, which I think everybody got correct, is Artemis. So Artemis is following in the footsteps of Mercury, Gemini, and Apollo. The Greek goddess Artemis is, I think, the twin sister of Apollo, so it's very appropriate for this. Number 3, what is the diameter of the primary mirror of the Nancy Grace Roman Space Telescope? Many people got this one correct, or very close to the correct answer. It's 2.4 meters. Number 4, Carolyn Porco directed Cassini to capture this photo of Saturn and Earth, which is titled "The Day the Earth Smiled." Most people actually got this right, which is surprising to me, but also good for everybody. I've seen a lot of people mislabel this as the pale blue dot because Earth is kind of a pale blue dot in the photo. But yeah, this is the day the Earth smiled. And there was a whole PR campaign organized around it where everybody was supposed to smile and celebrate at the time that Cassini was taking the photo. Number 5, the Leavitt law, named after Henrietta Swan Leavitt, relates which two properties of Cepheid stars? This is their pulsation periods and absolute brightnesses. It was also known as the period luminosity relation, and is one of the base rungs in the standard candle distance ladder that is used to measure the Hubble constant, and is part of that reason that there's a possible Hubble tension in cosmology. Number 6, which astronomer discovered that stars are composed primarily of hydrogen and helium? This was Cecilia Payne-Kapuskin. Some people put Annie Jump Cannon. They were contemporaries, but they accomplished different things. Number 7, which astronomer was awarded a share of the Nobel Prize in Physics in 2020? This was Andrea Ghez. Number 8, the 4th century philosopher Hypatia made several contributions to astronomy, including edits to this book by Ptolemy. The answer is the Almagest. Although I do appreciate the one person that put The Fault in Our Stars, which is a young adult romance novel. I think it's a little bit too recent to have been written in the 4th century, but I don't know everything. Number 9, the comet Shoemaker-Levy 9, named after co-discoverers Carolyn Shoemaker and David Levy, collided with which solar system planet? This was Jupiter. Number 10, NASA's headquarters in Washington, D.C. is named after which Apollo-era engineer? Most people got this wrong. It was not Katherine Johnson, who is the more famous of the women who the film Hidden Figures is based on, but it's actually named after Mary Jackson, one of the other main characters in that film. Number 11, while studying galaxy rotation curves, Vera Rubin found observational evidence for blank. Everybody that was paying attention to the first talk should have gotten this correct. The answer is dark matter. I know Dr. Carmona definitely addressed this in her talk. Number 12, which astronomer designed the canonical OBAF-GKM system of spectral types by which stars are classified? This one was Annie Jump Cannon. Number 13, Jocelyn Bell Burnell discovered which type of star? I think everybody got this right across the board. This was pulsars. Number 14, who is the first woman astronomer to go to space? Valentina Tereshkova. I actually got several people who apologized in the answer for not knowing the answer to this. don't feel bad. Not everybody knows it. But I do appreciate the one that put a nice Russian lady, which is technically correct. You didn't get points for it, but congrats for knowing something. Astronomer number 15, astronomer Andrea Ghez discovered that there is a blank at the center of the Milky Way galaxy. This is a black hole or a supermassive black hole. Either one was accepted. So the winner of tonight's trivia was the team Most Darkest Matter with 14 out of 15 correct. I believe the only one they got wrong was the Alma-Gauss that Hypatia contributed to. So thank you everybody for playing. And for the winner, I will contact you later this week about coordinating to get you your prizes. That I will give it back to Michael.
All right, thank you, Arvind, and thank you to everyone else. If Brianna and Jacob want to come back. Oh, there's one of them. All right, there's the other. All right, thank you all for coming out. It's been one interesting evening. We are on Twitter, we are on Facebook, we are on YouTube. Different ways to find us, different ways to follow us. So if you had fun tonight, please do take the time to follow us so you can like and subscribe and all that stuff. We will be back in April. April will be Jacob and my's last Astronomy on Tap, not just because of what happened tonight. We had planned this out previously. So come stop by. Hopefully you can say goodbye to us and enjoy another night of Astronomy on Tap. We don't have a date yet, I believe. So stay tuned to all those things that I just mentioned on YouTube and Facebook and whatever, and we will announce when we are coming back. So thank you all for coming out, and we hope to see you next month.